for 1.A, you don't have to know the law of octaves. That has been removed from the specification. Now, the spaces for undiscovered elements, the name of the scientist is Mendeleev. In part B, so we've got the outline of the periodic table, so you would have your data sheet in front of you. And then A is a gas which burns with a pop. Well, when you have a lit splint and you put it into hydrogen gas, you get pop. So A is going to be hydrogen, and hydrogen is up here. The least reactive alkali metal. Well, alkali metals are group 1. So that's this group. And metals get less reactive as you go up the group. So the least reactive alkali metal is going to be up here. That's lithium. So we'll label that B. The element in period 3, group 2. Okay, well, group 2 is here. And then period 3. Well, don't forget that hydrogen and helium, which is over here, are in period 1. And this is period 2, and this is period 3. So C is going to be in here, which is where you would find magnesium. And the last one, D, a metal which is a liquid. Well, there are 2 elements which are liquids in the periodic table. One is bromine, that's a non-metal, and the other one is mercury. So D is there. Part C. 2 elements in the same group. Now, atoms of elements in the same group have the same number of electrons in the outer shell. So when you look at the electronic configuration, you can see that Q is 281, so that means it has 1 electron in the outer shell. It's in group 1. And U also has 1 electron in the outer shell, so it is also in group 1. So the answers here are Q and U. Now, period 2. Well, the number of electron shells equals the period. Now, if you look at P, it has 2 electron shells, 2 and then 6. So that means that P is in period 2. A noble gas, for part 3, has a full outer shell of electrons, so that is going to be T. An alkaline earth metal is group 2, so that means it's going to have 2 electrons in the outer shell, and you can see that R has 2 electrons in the outer shell. That's the answer. Now, sodium is Na. Chlorine is a diatomic element, so when it's on its own, it's always written as Cl2, not just Cl. And then that goes to give sodium chloride. Well, sodium has a valency of 1, and the chlorine has a valency of 1, so it's just NaCl. That would be 2 marks. 1 for this side, 1 for this side. And if you've got 2 marks already, you can then get the 3rd mark, but you have to have 2 marks before you can get the 3rd. You can see you've got 2 chlorines on the left. We need 2 chlorines on the right. So we put a 2 in front of the NaCl. That has now changed the number of sodiums on the right. So we need to go and change the number of sodiums on the left. Part 2. A halogen which reacts even more vigorously with sodium. So the question is about chlorine. Now, if we look at group 7, there's fluorine, chlorine, bromine and iodine. And non-metals get more reactive as you go up the group. It's the opposite way to metals. Metals get more reactive as you go down the group. So, a halogen which is more reactive than chlorine is going to be fluorine. And we'll have to give the name. E part 1 is about a displacement reaction. So we've got sodium chloride and bromine. Now nothing happens in this reaction, and that's because, if you remember from part D, the reactivity of the halogens increases as you go up the group. Now bromine is below chlorine. So bromine is less reactive than chlorine, so it's not able to displace the chlorine from sodium chloride. So the answer is just bromine is less reactive than chlorine. Another way you could say it is chlorine is more reactive than bromine. And the symbol equation for sodium bromide and chlorine, well, sodium has a valency of 1, and the bromide, which comes from bromine, has a valency of 1. Chlorine, I said before, is diatomic element, so Cl2, and then the halogens switch places. So sodium chloride is formed along with bromine. Now it needs balanced. Put a 2 there and there. And this type of reaction is displacement, because one halogen displaces another. Okay, part F, and working out the relative atomic mass. So we can see from the spectrum that there are two peaks, one at 35 and one at 37. So that tells us there are two isotopes of chlorine. One has a mass of 35 and the other has a mass of 37. So when we calculate the relative atomic mass, the answer has to fall between these two numbers. So if you do a calculation and it's lower than 35 or more than 37, you've done something wrong. The other thing you need to check is what the y-axis is. So here we've got relative abundance. Now sometimes it's percentage abundance. If it's percentage abundance, you're going to divide by 100. But here it's relative abundance, so you just divide by the total relative abundance. So we've got a peak, which is at 3, and a peak which goes to 1, so that's a total of 4. So we have a peak at 35, so that's due to a chlorine 35, and it has a relative abundance of 3, and then we're going to add on the total mass of chlorine 37, and it has a relative abundance of 1. And we divide it by the relative abundance, the total relative abundance, which is 4. And that gives an answer of 35.5. Okay, question 2, part A. Name, not the symbol, not the formula, has to be the name. A weak alkali. Well, when you look through these, you'll see in reaction D, NH3, that's ammonia. And ammonia is a weak alkali. Name a salt, again name, of a transition metal from the equations above. Okay, so let's see. If we look through, nothing in A. Now B, a salt is formed when the hydrogen ions in an acid are replaced, when some or all of the hydrogen ions in an acid are replaced with metal ions or ammonium ions. So here in B we've got an acid, and it's reacting with copper oxide, and copper is a transition metal, and that will form the salt copper 2 chloride. That's the answer to part 2. That is a salt of a transition metal. Now you probably would get that correct if you just said copper chloride. However, it's good practice to put in the number in Roman numerals to refer to the valency of the transition metal. And we know copper has a valency of 2, because we need 2 chlorines for every 1 copper. Okay, so this 2, remember when we're working out the formula, we swap the valencies. So this 2, after the Cl, has come from the copper originally. So that means that the copper is copper 2. Okay, on to part 3. Chemical test for gas in reaction C. Okay, well the gas here is carbon dioxide. The carbon dioxide turns lime water milky. You do not say cloudy. You could say a white precipitate or a white solid because that's what the milkiness is. So we'll put in lime water. And when there's a change in appearance, always put in the colour at the start and the colour at the end. So lime water is colourless to start with, and then it goes milky. And as I said, do not put in cloudy. Now the salt, and again we're going to name it. In reaction D, so this is the salt because we're reacting an alkali with an acid. NH4 is ammonium, not ammonia, and SO4 is sulfate. So it's going to be ammonium sulfate. Now reaction E is neutralization. It tells us the ions which have taken part in the chemical reaction. So some ions are spectator ions. They don't actually do anything. So they're not of importance. Now you should know that neutralization and ionic equations are just always H plus OH minus goes to give H2O. It does not matter what the acid is or what the alkali is. This equation is the one you always write for an ionic neutralization reaction. So the H plus is from the acid, OH minus from the alkali, and then that forms water. Now it does ask for state symbols. All acids produce hydrogen ions when dissolved in water. All alkalis form hydroxide ions when dissolved in water, and then water itself is a liquid. Now you could look at reaction A as well and look to see what has actually changed. So look at the K on the left hand side. So potassium hydroxide is made up of potassium ions and hydroxide ions. And then if you look over on the right, you've got potassium chloride, which is made up of potassium ions and chloride ions. So the potassium ions haven't changed. You've got K plus at the start, and you still have K plus at the end of the reaction. So they don't really do anything. They're spectator ions. Now the OH on the left, well, you don't actually have an OH on the right. Those are hydroxide ions. So hydroxide ions have changed. Remember, so anything that is the same on the left and the right, they will cancel out. But if there's something which is only on one side of the equation, then that's what we need to keep. So we're going to keep the OH minus. And we'll have to write this as a charge because it's an ionic equation. Ionic equation always has charges. Now the HCl, well the Cl is chloride. Remember, acids produce hydrogen ions when dissolved in water. This is actually made up of H plus and Cl minus. And potassium chloride on the right hand side, that's Cl minus. So again, the chlorides haven't changed. They're there at the start, they're there at the end. They'll cancel out. So that just leaves the hydrogen ions. And you can see that you've got H, which is going to form H plus. You don't have H plus on the right hand side. There's going to be H plus. And then you've got water. So that's where the ionic equation comes from. But as I said, when you see a question and it's asking you to write an ionic equation for neutralization this is what you write. Part B. Balance sum equation for copper 2 carbonate. Well, copper 2 carbonate is CuCO3. The 2 tells us the copper is a valency of 2. And carbonate, which is CO3 2 minus, this tells us the valency. The 3 is not the valency. They both have a valency of 2, so it's just CuCO3. Nitric acid is HNO3. I'm going to get the salt, copper 2 nitrate, plus water, plus carbon dioxide. It'll need to be balanced. You can see that on the right you've got 2 nitrates over there. So we'll need 2 nitrates on the left. Just put a 2 there. Part 2, the colour of copper 2 nitrate is blue. Copper solutions are usually blue. The separation technique then used to separate excess copper 2 carbonate from the solution. When the copper 2 carbonate is added to nitric acid, you'll see fizzing and the carbonate will disappear. But if you add excess copper 2 carbonate, which we're told in the question, some copper 2 carbonate will remain unreacted and it'll just sink to the bottom of the container. Now we've got to remove that carbonate, and we would use this apparatus. So here we've got filter paper. This is a filter funnel, and then the excess copper 2 carbonate will get trapped in the filter paper. So this technique is known as filtration or filtering. Part 4. Now exothermic means gives out heat. So we've got to use a thermometer to measure the temperature, and to record that the temperature increases, we're going to need to measure the temperature at the start and then at the end, and we'll find that there will be an increase in temperature. Part C, a cation is a positive ion, and metals form cations by losing electrons. Okay, the chemical tests used to identify the cation, which is the positive ion, and the anion, which is the negative ion. It's formed from the non-metal in solid magnesium iodide. Now this word solid is important. It's in bold, and when you have a solid sample and you want to carry out qualitative tests, it's a good indication that you need to dissolve this in water before you can proceed with the tests. So first thing, I'm going to dissolve it in water. Or you could say make a solution of the solid. Now to identify a magnesium ion, we can add sodium hydroxide solution. It's important that you put in solution. And this will form a white precipitate. Or you could say solid. Now a white precipitate, a precipitate is just a solid that forms in a liquid during a reaction. Now magnesium ions are not the only cations to form a white precipitate with sodium hydroxide solution. Aluminium and zinc ions will produce the same result. So to determine and prove that they are magnesium ions, we need to add the sodium hydroxide solution until in excess. Zinc and aluminium ions will dissolve in excess, whereas the magnesium ions, or the precipitate that forms when added to magnesium salt, does not dissolve in excess. Now you may wonder if you could use ammonia solution. Well, ammonia solution will also produce a white precipitate with magnesium, zinc and aluminium ions. But when you add the ammonia solution in excess, the solution containing aluminium ions and magnesium ions will not dissolve. So we cannot determine which one is magnesium or contains the magnesium ions. So as I said, the aluminium and magnesium ions will produce the same result with ammonia solution. So that's why we add sodium hydroxide solution. So now we've determined the cation. The anion is the negative part, or the non-metal part of the salt. That's the iodide. Well, anytime you're trying to identify a halide, that's a chloride, bromide, or iodide, you use silver nitrate solution. Okay, always. So I'm going to then add silver nitrate solution, and again, need to put in the word solution. And when silver nitrate solution is added to a solution containing an iodide, you will get a yellow precipitate. The precipitate itself is silver iodide. Now you don't need to put this into your answer. That's enough there. But just to show you what this precipitate is, so you've got silver ions from the silver nitrate solution. The silver ions are what react. This is going to be an ionic equation. And they react with the iodide ions from the magnesium iodide. When these two ions react together, and they're both aqueous, so I could, if I was asked, I would put in state symbols to show that they're dissolved. But when they react together, they form a solid of silver iodide, and it's that silver iodide which is the yellow precipitate. Okay, the bond in magnesium, well, magnesium is a metal. So the bonding here is metallic. And then you just have to write down a description of a metallic bond. Just to remind you what that looks like. Here we have our positive ions. And if you're asked to draw this out, you would always label it. So remember, these are not protons, positive ions. And then you have your delocalized electrons. Those electrons are not fixed. They're free to move throughout the structure. The formula for magnesium chloride, well, Mg is magnesium, chloride's from chlorine. Magnesium has a valency of 2, so I'll swap it and put it after the chlorine. Chlorine's a valency of 1. Well, I don't need to put it after the Mg, so it's just MgCl2. Now, dot and cross diagram. So what you need to consider first of all is this the transfer of electrons or the sharing? Well, magnesium is a metal, and the chloride, which is from chlorine, is a non-metal. That means it's ionic. This is the transfer of electrons. When drawn an ionic bond, you draw the atoms at the start, the ions at the end, and then the charges. So now we have the atoms and ions drawn out. So we've got our magnesium and chlorine atoms. Now we've got our magnesium ions. So we can write Mg2 plus, or another way of doing it is put in brackets, for example, and then put in the 2 plus outside it. It's up to yourself what way you do it. And then over here we've got our 2 chloride ions. See part 1. What this question is asking you is to give 2 physical properties, not chemical properties. It's physical properties of an ionic substance. Magnesium chloride is an ionic substance, so you just need to be able to recall something like soluble in water. That's a typical property of an ionic substance. It's got a high melting or boiling point. You could say it conducts electricity when molten. Remember, ionic substances don't conduct when solid, but they do when liquid, because when they're liquid, the ions are free to move and carry charge. The conductivity has to do with ions, not electrons which is the case in metals. And part 2, another compound with similar bonding and properties to magnesium chloride. So you just have to name another ionic compound. So for example, sodium chloride. D is a dot and cross diagram for the bonding in hydrogen chloride. Well, hydrogen and the chlorine are both non-metals, so this here is going to be a covalent bond, the sharing of a pair of electrons. And when drawing covalent bonding, we only ever draw the outer shell electrons. So there's the hydrogen chloride, and we have to label a lone pair. Well, a lone pair of electrons is just a pair that is not involved in bonding. And you can see in the chlorine you have 3 of them. So I'm just going to label this one here. That's the lone pair. Now, part A is asking you to really compare a simple covalent molecule or a molecular covalent molecule, they mean the same thing, with an ionic substance, magnesium chloride. Now, simple covalent substances have low melting and boiling points, and that's because they've got weak van der Waals forces between the molecules. So if you think of hydrogen chloride as this, and I'll draw another molecule. So the bond between the atoms is a covalent bond, and that's very strong. But there are weak van der Waals forces between the molecules. They're weak, and they require little energy to break. So that's why all simple covalent molecules have low melting and boiling points. Magnesium chloride is ionic, and ionic bonds are very strong, and they need a lot of energy to break. Okay, so there you can see definition of solubility. And basically what that means is if you had 100 grams of water, it's always defined in terms of 100 grams of water, and we're seeing the mass, the maximum mass that would be required to add into this until no more dissolves, and no more just dissolves. So let's say we could add 20 grams, just as an example. So let's say 20 grams is required to completely saturate the solution, and no more can dissolve. So if you were then to add another 0.1 gram, it would not dissolve. It would remain undissolved. Okay, part 2, ammonium dichromate. Ammonium is NH4 plus. You'll see it at the back of your data sheet. Dichromate is Cr2O7, again it's at the back of your data sheet. And the dichromate, you'll notice, has a valency of 2. So we swap these over. Now ammonium is made up of 2 different elements, and we want to say all of this has a valency of 2. That the 2 comes from the dichromate. We've swapped it over. So we put the 2 outside the brackets, and ammonium, you can see, has a valency of 1, and we don't need to put in the 1 after the dichromate. There we have NH4 in brackets 2, Cr2O7. Take a look here. Now we're looking for ammonium dichromate. Okay, ammonium chloride and a solubility of 55 grams per 100 grams. So we go to the graph, look for 55, because that's the solubility, and just read across until it meets the ammonium chloride line. So you can see it's about there. If we go down, it's somewhere around the 59 mark, and you're generally allowed plus or minus 1. So I'm going to put in 59 degrees C, and I say you're usually allowed plus or minus 1 degree C. Okay, part 2. At what temperature do both salts have the same solubility? Well, that's where the lines are going to meet. So you can see that's it there. So if I write down that's 22 degrees C. And again, you're allowed plus or minus 1. Part 3. Why does the x-axis not go below 0 or above 100 degrees? Well, that's just because water freezes at 0 and then boils at 100 degrees C. Part C. So let's say a concentrated solution of ammonium dichromate so ammonium dichromate, that's this one. It's at 60 degrees C and it's not saturated. It contains 30 grams and 50 grams of water. Now that's important. We'll come back to that. It's then cooled from 60 to 20 degrees C. So what mass crystallizes out? Now when you do this type of question, you first of all work out the mass that would crystallize per 100 grams of water. These graphs, these solubility curves, are always per 100 grams of water. So you've got to work out the calculation based on that first of all. So if I have my beaker with 100 grams of water and it's at 20 degrees C, then I can work out the solubility of it. Now I'll remove this just to make it easier to see. And if you read off from 20 degrees C for ammonium dichromate, that's 36. So 36 grams can dissolve in 100 grams of water at 20 degrees C. Now, if 36 grams can dissolve in 100 grams of water, that means that if you had 50 grams of water divided by 2, therefore 18 grams would dissolve in 50 grams of water. Just to go over that again, we've worked out from the graph that 36 grams of ammonium dichromate will dissolve in 100 grams of water. Therefore, if you had 50 grams of water, 18 grams of ammonium dichromate would dissolve, because we've just halved it from 100 to 50, therefore we have to halve the 36 to 18. In the question, we were told that originally in the 50 grams of water, there are 30 grams of ammonium dichromate. So we start off with 30 grams. It's not saturated, so that means these 30 grams are all dissolved. And if we cool it down to 20 degrees and 18 grams remain dissolved, the difference is going to be what crystallizes out. So that's an answer of 12 grams. Okay, this question now is about empirical formula. So what I'm going to do is just do out a fairly rough table. So we've got carbon and hydrogen, nitrogen and oxygen. It doesn't matter that these are percentages. You just treat them like masses. So the mass is 20. Hydrogen is 6.66. 46.67 and what's that? 26.67. So we've got to work out the moles of these. So that's going to be 20 divided by 12, 6.66 divided by 1, and so on. So there, I've worked that out. And now you divide through by the smallest. Well, it's 1.66 in this case. So if we divide by 1.66, that's obviously a 1. It's going to be 4. That's 2. and that's just 1. The empirical formula is CH4N2O. Here we've got a reacting mass calculation. So we've got 5.1 grams of the hydrogen peroxide. So we've got to work out the number of moles of it. So we divide by the RFM of H2O2, which is 34, and that gives us 0.15 moles. You can see then that the ratio of hydrogen peroxide to oxygen is 2 to 1. So that means we're going to get half the number of moles of oxygen. That'll be 0.075. And then to work out the mass of oxygen, that's the number of moles times the RFM of O2, which is 32. And that gives an answer of 2.4 grams. Okay, here's just a definition of water of crystallization. The percentage of water of crystallization. Now, the way you work that out, look at the formula of the silica. What you've got to do is work out the RFM of the hydrated salt, and the RFM of that is 96. So the way you would do that is work out the SiO2 bit, and then you've got 2 H2Os. 2 H2O is 2 times 18, which is 36, and you just add that on to the SiO2. So we've got 2 H2O, as I said, that's 36. So that's the total mass of the water. We divide that by the RFM of the hydrated salt, which we've already worked out to be 96. And then we times that by 100 to get a percentage, which is 37.5. Now silica, and for part 3, has a structure similar to diamond. What is this? Well, diamond is giant covalent. So silica will have a giant covalent structure. Now this time we've got to work out N, the number of moles of water of crystallization, or the degree of hydration. So what I'm going to do, again, draw out a table that's a bit like we did before when working out empirical formula. And what we've got to do is work out the number of moles of the dry or the anhydrous aluminium oxide and the number of moles of water. Now it's important that you use, or that you remember, that the aluminium oxide has to be anhydrous. So I'll just put this in. May help you to remember. This has to be it when it's dry, after it has been heated to constant mass. That means that the mass does not change any further. So we start off with hydrated aluminium oxide, which is 3.12. And when it's heated to constant mass, 2.04 grams of the anhydrous aluminium oxide remained. So the question is telling us that we've got 2.04 grams of the anhydrous aluminium oxide. So we can work out the mass of the water. That's going to be 3.12, which is the hydrated aluminium oxide, and we subtract the 2.04. That's the anhydrous. So the difference here is going to be caused by the water of crystallization. So that equals 1.08. Then have to work out the number of moles. So the RFM of aluminium oxide is 102. That's 0.02. And here it's 1.08 divided by the RFM of water, which is 18. And that works out to be 0.06. We divide through by the smallest one, which is 0.02. That gives us 1 to 3. So n is equal to 3.